Okay, hello everyone. What we're going to do here is start to take a look at how we can potentially deal with some different thermal boundary conditions. So, kind of as far as like big high level categories we've looked at principally subsonic flow around an airfoil. We've looked at principally supersonic flow around a double wedge, um, things of this nature. We also looked at convergent internal flow through a nozzle. What we're going to look at now is sort of kind of hybrid almost interior exterior flow through kind of what is going to emulate sort of heat exchanger plates. It's going to be 2D. Keep it simple. Um, but we're going to look at thermal conditions. How do you look at thermal conditions? How do you measure thermal conditions? How do you apply thermal boundary conditions to a flow? So, hold on a second. There we go. Make it a little bit more visible for everyone. So, how are we going to do this? What we're going to do is we're going to want to effectively emulate flow through, ahead of, through, and behind kind of a plate type or closed fin heat exchanger. Again, it's going to be not a precise match because this is going to be 2D, but we'll do our best. So, what we're going to want, we're going to do this a little bit differently. We're not going to use, cones, blocks, cylinders, what have you to build this up. We're going to build this in 3D CAD. Um, my suspicion is it might be a little bit easier, but I don't know how much easier. We will see. So, we are going to create a rectangle. These are going to be our fins. So there's a rectangle. These are going to be relatively small fins. Apply length dimension. It is going to be small in that. We're going to make these. Oh dear. Pretty small. How small is pretty small though? Let's go with 1 millimeter. That's 1/25th of an inch, give or take. Right. That's actually pretty thick for a heat exchanger plate. Um, but it's also pretty thin to be able to mesh relatively easily. So we're gonna do. Let me think here. Typical heat exchanger might be 3 or 4 inches in thickness. So we'll do 80 millimeters. So 0.08 meters. And actually, we'll parameterize these. This is a little bit more advanced. Don't worry about that part. I just might utilize the simulation later to demonstrate a couple of things. So we're sort of future planning here a little bit. Let's see here. And then we want to do here is I'm forgetting where the heck I put it. I'd like to pattern this. But I'm forgetting. Oh, we're in a sketch. Duh, we can't pattern things in a sketch. That would explain it. Okay. However, I believe this entire thing is capable of moving still. So we want to constrain this a little bit. So what we're going to do is we're going to put a point here, and we're going to tell it that this, so we're going to select the point and the line and say, hey, that point, you're at the midpoint. We are going to constrain this point to 0, 0, and 0, 0. Let's see if it does it exact. And we are going to fix this point. And this should be pretty much incapable of moving now. It looks like it's tilted a little bit because the entire screen is tilted, but this is incapable of moving. So, how are we going to do this? We probably want a... keep on clicking and doing that one. That's really not what I want. We probably want a simulation domain here. So we want a couple of things. We want to dimension the difference between these two. This is kind of our run-up. So apply a distance constraint. This is going to be run-up distance, and we're going to call it as, well, I mean, the fins were 0.08. So we'll call it 3 times that. 0.24. So we're going to have flow through there, and then we'll do the same thing at the back. I'm still going to parameterize it, but, or as a different parameter, rather, I'm going to parameterize it, but 3 times 0.08. Okay. Oh, I'm forgetting some very important things here. Hold on a second. Let's edit this. And same deal. We're going to put a point here. We're going to put a line that connects these two. This is going to be a construction line. This is going to be a horizontal construction line. And this point, at one end of that line, is going to be midpoint constraint for this larger rectangle. So this should be fully defined now. Or, sorry, not fully defined. We can still modify this. So let's apply a link to that. 0.15. Stack thickness, stack height. Yeah, sure, we'll go with stack height. There we go. Okay. Let's see here. And truth be told, I might have messed this up a little bit. Yeah, pretty sure I messed this up a little bit because this exterior rectangle really shouldn't be here. So I'm going to just set those as construction. So they're effectively not going to do anything now. We're going to take sketch 1, rename it. Let's see here. There we go. Call this a fin. We are going to extrude this. 0.1 meters really doesn't matter which direction because this is going to be a 2D simulation. But there's one of our heat exchanger plates. We are going to take our body group and we are going to pattern it. We are going to do a linear pattern in X and negative X, incidentally. I don't know if this will actually work. Let's see here. Oh, no, I want this to be in Y. 0, 1, 0, and 0, -1, 0. So in one of these directions, it includes this. Interesting. Okay, so you can see in one of these groups, specifically this one, I believe. Oh, maybe not. That's curious. Hold on. Okay, you know what? We're going to do this a slightly different way, and say that no, this is just the this is the stack height. So how do we want to do this? Reference coordinate system, number of instances. So that is going to expose us as just the stack height. Expose this as bin count. And this is going to be like 0.05. Oh, no. That is pretty small. So if these are a millimeter thick, they have like 10 millimeters between them. So it's 50 millimeters. 2 inches, 20 fins. Uh, why is it making this longer? Oh, yeah. Okay, it's not the total thing, it's the... This is more reasonable. So let's do something like 20 fins. 20. And if we do them 8 millimeters apart, 8 millimeters apart, I said. That's probably a reasonable-ish approximation. Okay. Okay. So we have our fin stack. Now we need to, on the XY plane, create a sketch here. So we need to do a couple of things probably. We want to create primarily our domain, which we're going to cut these fins out of. So we're going to create a rectangle and then we'll position said rectangle appropriately. So in order to do this, can I project? Yes, I can. Okay, so we're going to take our primary fin and reference everything off of this. Oh, hold on a second. I should probably hide pretty much all of these. There we go. Let's go back and edit this sketch. There we go. Okay, this will make things a little bit easier. Just a little bit. And actually, I should probably edit my original sketch because the way I defined this is slightly incongruous with how I want to do this now. So order of operations matters. So, yeah, we'll do it like that. Go back to this sketch and edit it. We should see, yep, that our offset line, the bottom corner, is now at the origin. Okay. So we still have our thing. Let's do a couple things. First of all, we'll do a length dimension here, or a distance dimension. This is going to be the fin to wall distance. This is going to be interesting. So we need the separation between fins. I don't know what this number should be right off the top. We're going to have to do some math to figure out this one. So I think we had 20 fins. I put them 8 millimeters apart. They're 1 millimeter thick, so 9 millimeters per fin, and I put 20 fins. So that's 180 millimeters plus distance on either side, so 0.208 meters. So domain height. This is our run-up distance still. 0.08. Done. This is going to be our run down distance, same as before. I'm going to say 2 because I already named one that, but that's okay. I think this is fully constrained now. Okay, so click OK. We have our sketch. We will extrude this. Again, 0.1 meters one way is fine. And then we can do let's see here, solid primitive. Okay, that's just making solid primitives like that. Let's see, roll back. Oh, okay. There's an issue here. I had it make this block, but because of the way I had it make it, it kind of absorbed all of the other. It absorbed all the fins really. So if we select all of these, Boolean subtract, target bodies is target body is going to be body 21. How do I change this? Remove all. Body 21 is the target. And everything is the tool, as it were. Oh, no, crap. Body 21 is that. Everything is that. Okay. Why did that not work? Maybe it doesn't like... Oh, I think this subtract works slightly differently from the other ones. So I think it doesn't want body 21 to be listed as a tool body. Yeah, there we go. Yep, look at that. That's better, sort of. Design parameters. So, domain height actually wants to be some combination of things. It wants to be the thin separation times 0.5 due to the initial separation. It wants to be plus thin count times where is it? Thin separation? Maybe just that, honestly. I'm a little bit curious exactly what that distance is. I wonder if I can measure it somehow. Let's see here. Is there a measure tool right here? Measure. Minimum is 3 millimeters. So we're almost there, but not quite. So what we want is we need to just add another fin thickness to this, I think, is what's going on. If we add one fin thickness, we should be good to go, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 18, 19, 20. We do have 20 fins. So, I'm going to close that. Our domain height probably just wants to add $sign fin thickness. Date added just a little bit. So that looks about right. Yeah. Update 3D CAD. Replace face. Body features. Okay, so we're gonna call this inlet. Let's see if this works. This is I usually don't use 3D CAD, so this is a little bit new for me in a lot of ways. We're playing it a little bit by ear. Yeah, that really doesn't work. Wait, what just happened there? Yeah, that's an inlet, all right. That's called outlet. Which one of these? So I think this is going to be plane because this is a simulation plane. I think this is going to be out of plane, have our outlet. So, hmm. Oh, I broke my sketch. How'd that happen? Probably by doing exactly what I expected to do. It doesn't like dimensions that are 0. So we're actually going to delete this dimension. And we're going to make this coincident with that. And you'll see why in a second, I think. This works the way I expect. Which it might not. 3D CAD. Okay, so show only that. Okay. What I want is probably to change the domain height so it's actually fin count -1. We're going to update again. Oh, wait a second. Something didn't quite compute. Oh, we don't need the plus fin thickness either. Okay. Why isn't this updating? Edit. Let's see here. Okay, so this is currently evaluating out to 0.156. Oh. Maybe it just needs to be smaller? Hmm. Try it. Oh, I know what's going on. Yeah, that would make sense, sort of. And then we also need to lose. We need to lose that, and this can be -1 again, I believe. And then minus fin thickness. Update. Perfect. Okay. So we're going to just modify this, and we're going to say imprint is true. Update. So what do we have here? Okay. So now effectively we're also modeling a fin here because this face is going to be separate. You can see that I can click left, click right, and click center, and there are 3 separate surfaces. Okay, I think that's what we need right here. Rename is air. Rename. Can I not bulk rename in here? That's annoying. Okay, whatever, fine. Let's see here. Close. Okay. Close 3D CAD. Now we have several bodies. And mostly what we need to do is we need to take the air out. Okay. And we have several surfaces already. This is pretty good. Well, I might need to go back and rename them a little bit. Let's see here. Default is going to be everything. Yeah, I need to go back and rename them a little bit. Okay. So let's go back in here, edit. We're going to call these run up wall. Call these, rename, run down wall. And everything else by default is going to be the fins. Named faces is going to be fins. Okay, 3D CAD, close, and if we say update, does this work? It does. Default still exists, but it's empty. We have fins, which is all this stuff in the middle. Perfect. We have inlet, we have outlet, we have out of plane, we have in plane, we have the rundown region walls, and the run up region walls. Perfect. This is exactly what we needed. So operations, new, surface preparation, mesh, badge for 2D meshing. Time to badge the air for 2D meshing. We need to create a region out of this. Appears to have worked beautifully, by the way. It properly recognized our plane as our simulation plane, our out of plane is out of plane, default is nothing because it doesn't exist. All these are boundaries. Perfect. This is exactly what we want. So now we have our boundaries. We have our fins, we have our inlet, we have our outlet, run up, run down. Perfect. So our fins are a wall. This is going to be a velocity inlet over here. This is going to be a pressure outlet over here. These are going to be just walls. We'll select our physics in a minute. Operations new, mesh, automated 2D mesh. We're going to mesh our air with a polygonal mesher, prism layer mesher. We definitely need a prism layer mesher. Okay, our base size is going to be small, relatively small. Our base size is actually going to be 1 millimeter. Number of prism layers, we're going to want, let's say 6. Prism layer total thickness, 25%. Prism layer stretching, that's probably okay. Surface proximity, we're going to want at least 6 cells in between these plates. And we're going to put a search ceiling on proximity of 10 centimeters, so it should only find these plates. It's only going to worry about things that are closer than 10 centimeters to, or 10 millimeters, excuse me, to each other. Minimum surface size, we're going to drive that way the hell down. We will let it get small. Actually, we don't need to let it get that small. 1/10 of a millimeter should be fine. Target surface size 100%, that's fine. Custom controls. So let's do a couple things. Let's control the entire domain max size. And we will control this to 8 millimeters, so 800%. We will do a surface control on the inlets and outlets. which we're going to have it target. We'll go with 400% of the base size for the moment. That might need to go up or down. Inlet, outlet, refine. Well, it's actually a coarsen, but it's still considered a refinement, so to speak. Or not really. Inlet, outlets. We'll call it what it is. It's a control. We want to disable any prism layers on these. That's fine. We also probably want to coarsen up the mesh on those surfaces. So we'll add a new surface control. This is going to be our wall control. This will have a boundary layer. So we will customize some aspects of that. We'll customize definitely the total thickness. Minimize, or the target size and the minimum size. We'll let this be twice as big. Not like stupendously big, but, you know, bigger. And we're going to kick up the prism layer size to kind of suit. And it doesn't need to be any smaller than 0.5 millimeter for that. This might take a while. So let's see here. This PC, we'll just put it on the desktop for the moment. In simulation, I should have saved earlier. Save more often than I'm doing. Do as I say in this case. Don't do as I do. Save more often than that. Oh, that was fast. That's curious. Let's see what this looks like. Not even bad, honestly. Not even bad at all. Holy crap. Prism layer. Prism layer thickness can go up. Oh, I didn't actually refine the walls. Run up, run down wall. I made the control. I never actually refined it. Prism layer total thickness. Let's make this 50%. And I'm liking the max size coming down by a factor of 2 as well. Also, in general, the growth rate should probably be smaller. So we're going to customize the growth rate to 5%. We'll try that again. I kind of don't like what it's doing up here. This, I'm not the biggest fan of, honestly. So what we're actually going to do is on the fins, new surface control, rename. We're going to knock down the target size by a factor of 2. Except I didn't actually select the fin, so it didn't do anything. Alright, let's try it again. I'm more okay with this, but still not particularly happy with it. But we'll call it good and see what the simulation does. So we have our fins here. So we have, this is where our heat's going to come from. So let's go ahead and define some physics here. Select models. It's going to be a steady flow. It's going to be a gas flow. We could do a liquid heat exchanger, but we're going to do a gas. We're going to do segregated flow. We are going to be adding heat, but we're not going to be adding a tremendous amount of heat. But we are adding heat, so it does need to be an ideal gas. We're going to make it turbulent. We're going to make it K omega turbulent. We are going to include gravity because buoyancy effects can and will matter in natural convection driven flows. We're going to start with forced convection, but we might turn forced convection off and have it become natural. By manipulating boundary conditions. So let's set some reference values here. Gravity is in the negative y direction. That's fine. 1.18 should be our standard reference density based on our reference pressure and starting temperatures. That is, if air comes in at 300 Kelvin, it's going to be at about 1.18 kilograms per cubic meter. So the only thing we're really going to change here thermally is we have our inlet boundary condition. It's going to come in at 300 Kelvin. That's fine. It's going to come in at what's a good number? 5 meters per second. How about? Not super fast, but definitely not super slow either. Outlet pressure is that's fine. This outlet pressure and temperature is only going to matter if flow comes back in through here, so that should be okay. These can be adiabatic walls. That should be fine. So remember, by default, every wall is an adiabatic wall. It does not allow heat flow through it. However, we can change it from adiabatic to several potential heat sources. So we're going to change our fins to what is known as a total heat source, or just a heat source. You tell it, I want some number of watts of dissipation. Let's do, and this is about as big as a CPU heat exchanger, except it thinks it's 1 meter deep, which, it's not in reality. So it's probably about a tenth of that. So we're actually going to kick up our total heat source to 2,000 watts. About 10 times computer processor size, because this is about 10 times the area of a typical computer heatsink. Order of magnitude. And see what happens. So how do we want to see what happens? Well, first off, we can look at a couple of things to see what's going on here. Let's go ahead and look at what is the trick. Let's look at the surface average temperature on these fans. On these fins, excuse me. Surface average temperature. Right now it should be undefined because we haven't run anything. We're also going to want to plot this average temperature. And we're going to want to make a scene probably with the very same, right? And I'm also going to make a vector scene of the same. A vector scene of temperature. That's probably not going to make a lot of sense when you think about it at first, because wait, temperature is a scalar quantity. Oh, I'm hitting refresh, not rename. Rename. But let's go ahead and create a vector scene for a second. Rename. Temperature vector. Well, what we're going to do here is we are going to plot temperature, but we're also going to do it in the line integral convolution way. So instead of plotting with a vector magnitude, which is the default way to plot vector fields, we're going to plot with a scalar field. So effectively, we're going to be plotting two fields. We'll be plotting velocity, and we'll be coloring it with temperature. Go ahead and click save. We'll initialize. And we'll see if this works. Yeah, seems to be. there we go. So you can actually see, you get a tiny little, well, here we have a kind of almost tiny separation bubble at the very edge of the fin. But by and large, you know, start with a relatively thin thermal boundary layer, and it grows over the course of this fin until it reaches the end and it flows downstream. So we can do some basic math potentially to verify this, but at this point, this should be giving off exactly 2,000 kilowatts. 2,000 kilowatts. 2,000 watts, not 2,000 kilowatts. That would be a lot. 2 megawatts of electrical power. Whew. Thermal power, rather. So this is roughly the same, give or take, as a kind of moderate CPU processor. Honestly, it's actually probably running a lot cooler than that would, because I don't know how fast a typical computer fan will move flow, but I don't think it's 10 miles an hour. It might be, and I might just not know my orders of magnitude for that. But I think this is probably a little bit faster than normal computer fans move flow, and I also think that I'm approximating the area pretty greatly. But we can pretty clearly see that we're dumping heat into this thing, and temperature is rising. Specifically, let's see, temperature is rising to a surface average of 316 Kelvin. Okay, that's pretty decent. Let's see if we can figure this out a little bit more exactly. We want to know, let's say we want to know what the maximum temperature is on these fins, right? This arguably could be more important. The fin maximum temperature, is going to be, let's see, oh, what I asked for a co-located field function. Sorry. We're going to ask for the maximum temperature, and we're going to ask for the position of said maximum temperature. We do not need to ask for the temperature at the location of maximum temperature. Or, yeah. Okay. There we go. So we can see, oh, wait, no data. Why is there no, oh, because I haven't told it what to look at. Fins. Click. Done. Okay. The maximum temperature is about 225 Kelvin. So it's risen by 25 degrees Celsius or Kelvin, depending how you look at it. Not much of a surprise. The location of the maximum temperature is basically at the end of the fin. It's let me think here. Is that basically the end of the fin? 0.08. Yeah. Yep. It's at the end of the fin. Because these fins are 80 millimeters long, right? So 0.08 or almost 0.08 is almost 80 millimeters. So it's at the back of the fin. We can, you know, just logically intuit from basic physics knowledge that that's correct. And we can see that the maximum temperature is, it's, you know, it's in here somewhere. Probably actually one of these at the top or bottom. So let's try something slightly more advanced. Let's do a line probe. And we're going to do this line probe more or less on the middle fin here. So let's get a pretty approximate idea. Let's see here. This thinks it's at going to be at height 0.0. Yeah, so that's probably pretty gosh darn close. So we want the same thing over here. So this is basically immediately below the surface of this fin. Right here. So we're going to take 40 measurements along the surface of this particular fin and see what the temperature looks like. Great. I also want to test something. Let's see. 0.07. If we put another probe of the exact same length right in the middle here. So I want to create a new XY plot. All right. This isn't technically temperature because this is just a probe. This just tells you where you can measure things. So let's see. Plot. Scalar function wants to be temperature. Yep. There we go. Here's our scalar plot of temperature. We're plotting position. So that's below. So if we drop within, yeah, we really don't get any values for the within one. But we get a temperature plot from the value below. Let's actually extend this below slightly upstream and slightly downstream. So negative 0.01, let's say. Yep, so no surprise, in front of the fin, we have 300 Kelvin. It hasn't interacted with it. Temperature hits the fin, jumps noticeably. We actually have a little temperature drop here, but then it starts rising, and then it reaches the end of the fin, and it drops off and falls rapidly. Not all the way back to ambient from what we're looking at, but it starts to approach ambient, right? It's never going to quite get there, honestly. So we'll do that. Say. So we can look at how temperature changes with distance over one of these fins. We could also potentially take a look at, let me pull up temperature scalar, which one of these fins is effectively hottest by looking at what is the maximum temperature on these fins. Well, let's go ahead and do this relatively quickly here. Probe, a line probe. So we're going to start. That's going to be our end point. It's going to be the bottom. Well, actually, the end point is going to be the top. The beginning point is going to be the bottom. So yeah, 0.0801. Sure, that's fine. 0.0801. That's fine. We want to start from basically nil. 0.0005. Oh, technically we're starting slightly above it. Yeah, that's right. 0.001. 11. There we go. And up here, 0.0148. Oh, no, I knocked off a decimal place when I shouldn't have. That's 149, 152. Okay, 152 is actually it. So we're gonna do 19. There we go. Actually, if we go slightly beyond, okay, and we have 20 fins, so we're going to do a 20 resolution line. So this should theoretically put one of these points just... Oh, no, not quite. You can see they're walking. There we go. This consistently puts a point just above and behind all of these fins. So this is a little bit of an approximation here, but I'm just kind of looking to see how close they are. And it looks like they all have pretty even spacing. They're all just off that diagonal. So what we're going to do here is create a new XY plot. And it's actually going to be plotted with respect to Y. So 0 space 1 space 0. A Y type value is indeed on the left axis. It is going to be temperature. We're going to pull this line probe. Okay, so it's a pretty even span in max temperature. We do have an outlier at the top. The bottom doesn't really appear to be an outlier. So we have a pretty even spread of temperature vertically. And of course, horizontally, the temperature increases pretty much linearly. So let's go ahead and change our boundary conditions a little bit. We are just adding a fixed amount of heat, right? Well, we can also tell it, no, that's not the way this works. This isn't a heat source. This is a fixed temperature. Fixed temperature of, I don't know, 118 degrees Celsius, give or take. More or less what that is. Click OK. Well, now the air temperature here is, not quite 400, but close, right? The air temperature just behind these things is, again, not quite 400, but it's up there. We have 388, we have 391. This is a pretty tight spread of temperatures. And the temperature in general is just a lot higher, really close to these. Now, what? Well, yeah. So that's kind of one of the other boundary conditions. You can tell it, hey, I know this much power is coming through here, like you have an electrical chip. And you say, okay, I know this thing uses 5 watts of power. Okay, 5 watts, it has to go somewhere, so it has to go into the air. What is the temperature of this thing? That's a great use case for a heat source. A static temperature is when you know that this thing's going to be at a temperature, and you want to know, like, what is the temperature distribution in the fluid. So it depends what you know, what boundary conditions you know. Maybe you know you have a heat flux. You have so much wattage per unit area. So let's do something that might be a little bit crazy. 20 kilowatts per square meter. Oh, my thing hit the stopping criteria. 1 second. Let me just turn off the stopping criteria, because we are going to iterate this a lot more. That's getting mighty toasty. That's well over 1,000 degrees Kelvin, or 1,000 Kelvin. Yeah. Our maximum temperature is like 1050 Kelvin. That's that's toasty. That is real toasty. Okie doke. We're just gonna, and the surface average temperature is obviously lower, but the maximum temperature is a little bit over 1,000. Um, did I ever plot the maximum? I don't think I did. Oh, the maximum temperature is actually almost 1,200. Now that we look at this, and it's still rising a little bit. It's slowly figuring out what's going on. Ah, that's okay. That's basically not rising at all. But go ahead and stop that. So that's a heat flux, right? It's very similar to a heat source, except it's just heat per unit area. So if you know your area, so in this case, if we take a metric for, I don't want frontal area. I just want a measure of area. So if we do a sum of area on all of the cells, area magnitude, on our fins, we should get a representation of what it thinks the total area is. So it thinks we have 3 square meters of area, which could check out. We have like a tenth of a meter times 20-ish. They all have top and bottom surfaces, and they're 1 meter deep. So yeah, that checks out, about 3 meters. So we're rejecting like 60 kilowatts of power through this thing. That's a lot of power. That is a lot of power in a very small area, comparatively speaking. But those are two types of boundary conditions. You can set a temperature, you can set a heat source, you could set a heat flux if you know what is your heat per unit area. You could also tell it, okay, back to before adiabatic, there's no heat flow. Or you can tell it convection. Convection's a little bit interesting. Now, convection's a little bit counterintuitive because you might be thinking, oh, hey, this is the convection between this wall and this surface. It's not, actually. What the convection thermal boundary condition assumes is that you have a wall. So this black line, you have a wall. It's figuring out what's happening on this side of the wall. You're telling it on this other side of this wall, so somewhere in this white space, there's another fluid at some temperature interacting with some heat transfer coefficient through a wall with some thermal resistance. So if you have an insulated wall on, I don't know, a house, you know the air temperature outside is, blisteringly hot, 120 degrees Fahrenheit. And you know some value of insulation, so like, I don't know, 0.05, 0.1. I don't know how reasonable that number is. Um, but let's assume that that's correct for a second. 120 degrees Fahrenheit, and it's natural convection, so it has a heat transfer coefficient of reasonably high. We'll call it like 12. Well, it's obviously not going to be, 1,000 degrees Celsius or anything silly like that. The temperature is working on bleeding its way out here. And we get a couple degree rise here. Right? As far as it's concerned, based on the insulation properties, based on the temperature of the air inside of the fin, clearly this is somewhat non-physical. There isn't room for air to exist in there. But you're telling it that on the other side of this wall, there's some fluid at 120 degrees Fahrenheit with this heat transfer coefficient, and the wall has this thermal resistance. That is what the convection boundary condition says. Now, let's take a small change in tack, and we are going to not use a inlet boundary condition at all. we're going to use pressure outlets all the way around. There is no forced convection here. And we're just going to say, hey, these fins are dissipating like 2 kilowatts again. Remember, we turned on gravity. Oh, I didn't want, sorry, I did not want a temperature. I want a heat source. Yep. Let's see what happens. As it tries to figure out what's going on here. Ooh, actually, better yet, we could change the direction of gravity. Right now, gravity's up and down, so clearly this is going to be rather unstable, right? Because air is trying to interact with perfectly horizontal plates. Like it's working on it, but it's having a hard time figuring out how to do this. It's kind of doing this like zigzag path thing through these plates. Let's go up and take a look at gravity and change the gravity direction. So instead of negative y, it's going to be negative x. Aha, now this looks more reasonable. So these plates are obviously heating up, flow is moving through them, and you're getting the hot flow rising. You can see it's still, it's definitely turbulent, but as the flow moves through here, it's actually accelerating, so you get this contraction in area due to the heating effect and continuity. So this is the equivalent of like a vertical fin heat exchanger letting flow through it. So last but not least, I mean, there's bazillions of things, but those are some of the big boundary conditions that we have. I don't know why it thinks this needs to remesh, but let me go ahead and rerun that real fast. So what I'm going to do here is we're going to set gravity back. Yeah, we're going to set gravity back to the way it was. So 0, negative 9.81. And we're going to leave this as a heat source. We're going to change, well, first of all, we're going to turn these boundary conditions back into walls, adiabatic walls. And our inlet is going to become a velocity inlet again. And what we're going to do is we're not going to vary the thermal dissipation. We're going to vary the velocity. Right now it's 5 meters a second. Let's go down to 1. Now it's definitely trying to figure out what's going on here. Once it figures out what happens with these fins, we ought to get a better idea of kind of how the temperature is changing here. Yeah, so those are kind of sliding back into family. Let's see here. Temperature scaler. Okay, so like take a look at roughly how thick this thermal boundary layer is, right? It's reaching a good way. I mean, depending how you want to look at it, technically the thermal boundary layer is, very thick. So let's turn up the velocity a little bit to 2 meters per second. Oh, hey, look, the thermal boundary layer thickness just changed considerably. 3 meters per second, something crazy, 10 meters per second. Right, now it's got barely any thermal boundary layer at all, right? Yeah, so it's getting to the point that down here at like 1 meter per second, natural convection is getting as powerful almost as the forced convection is, and is actually starting to be capable of driving flow backwards through these fins if there's a reason for it. But you can see that very clearly the air temperature on the right hand side is higher than the air temperature on the left. We could actually look at, let's see here, what would be a couple of other good averages to look at would be some surface averages. So let's look at the, stop this from iterating for starters. We're going to copy these. So these are both going to be temperature. Let's see here. This is going to be the inlet. This is going to be the outlet. And inlet and outlet temperatures are good ones to keep track of because those are kind of your bounds, right? You know what's happening at the inlet and the outlet. You can kind of cross-check that, oh, hey, yeah, you are actually adding, 2,000 watts or whatever to the system. Or temp inlet, temp outlet, and I'm actually going to change all of these to Celsius instead of Kelvin. But yeah, if we create a monitor plot from this, our inlet is, down here at 300 Kelvin, whatever that is, 26 something, 26.65 according to this. And our outlet's up at 38.1225. We could change our dissipation. Let's crank up 4,000 watts. So the difference should roughly double. So instead of increasing by about 11, it's going to increase by about 22, give or take. 38 up to 49. Oh, hey, look, that's about a doubling in this temperature difference. Bring this down to 1,000 watts. We should see it land right around 32-ish. A little bit more, 32.5-ish. So let's see here. Where are my residuals plot? So this is a fairly simple case. We're only dealing with fluid temperatures. One thing to note, if you deal with solids, those temperatures tend to take a lot longer to stabilize. A lot longer. Like your residuals might even completely flatline, but your solids could still be changing temperature. Fluids generally will adjust pretty quickly. Solids, not so much. So again, this is just kind of a crash course in specifically some of the thermal boundary conditions that we have and things of that nature. So that said, that's kind of like the core of it. I'm going to, for the purposes of AE 169, if the basics and what you're expected to do in class is all you care about, you can go ahead and stop here. I do want to try one more thing, which is to add in the solids. The solid fins and actually model them explicitly as solids. Perfect. Okay, so we have a whole bunch of different contact patches, which is kind of what we wanted. Let's see here. So these fins, I bulk rename them. Yeah. Fin, and we're gonna have fin 1, 2, 3, 4, blah blah blah, up to fin 20. Um, we have a whole bunch of contact patches for these fins. That's fine. We're going to actually create distinct regions for these. And also, can I have it update? Really? Okay, we're going to delete that. We're just going to recreate all our regions really fast. So we have all of our parts. Oh, actually, badge for 2D meshing. We're actually going to badge all of these for 2D meshing and see if that works. Execute. Oh, okay. Hold up. Hmm. Okay, hold on a second here. Let me go up into 3D CAD and do a small edit to maybe make life a little bit easier. Named faces, we're going to show this for starters. Show only. Rename. Why don't I have... Okay, that's a little bit interesting. And because I patterned this, it didn't inherit. That's unfortunate. Yeah. Okay, we're going to roll back to here, I guess. Roll forward. Delete our fin pattern. Why not delete that? We're going to create, we're going to take this body and we're going to pattern it again. So we're going to do 20 copies. They will be, actually, I'm not going to expose that pattern. because I want to do this. Okay. And this is going to be maybe I do need to expose that pattern, that value. Oh man, I'm just trying to do some solid. Trying to the word I'm looking for. Use some solids. Oh, hey, my named face has disappeared. Okay. Then plane. Then front. And top. And, nope. There we go. And back. And I don't think we really have the far side for some reason. That's a little bit curious, but I'll go with it, I suppose, for the moment. And create, okay. So we're going to pattern a linear pattern in the positive y direction. There will be body interaction, none. Okay. Now we want to actually utilize. So this is going to be fin separation. Okay. This is going to be fin count. Okay. Update. We have a whole bunch of them. Did it inherit names? They did. That's what I wanted. Perfect. Okay. That's the entire reason I did that. And now we're going to update 3. We're going to roll to end. And our domain create. And then we need to do a subtract. So we're going to Boolean subtract. Target is air. We're utilizing the fins. Keep and imprint precise. Transfer names from faces. That should be okay. Update 3D CAD. Close 3D CAD. And then update. Can I update this? Update. Why won't it update? Oh, it did update. Okay, perfect. We have a bazillion fin contacts. Why aren't they showing up? Fin back, fin bottom, fin. Oh, I got those backwards. Whatever. There's some other semi-random surfaces. Fins top, inlet, outlet. Oh, okay. What happened here is that these fins actually quite know what happened here. So where's my geometry? Give me back, well, everything. and only show me geometry. That's interesting and problematic. The fact that it doesn't have those surfaces. Hold on a second. Edit. Name faces. Yeah. Going up, down. Let's try this again. Update. But inlet, fin top. So I got all of these backwards. Like the top is the bottom is the top. But that's okay, mostly, I think. We'll make it work. But we do want to split by contact. Oh, maybe not. Okay, tell you what, we're actually going to roll this all the way back, which is a sign why you might want to do your prep work really well the first time. So we're going to inherit all of these. New geometry part. Create part contact. Yep. Okay. Parts. Air. Part surface. Fin back, fin front. Yep. Up, down. Yep. Okay. That's what we needed. So, for starters, we're going to split all of these fins by contact part surface. We have a bazillion contacts now. We made about 80 contacts. Not quite 80, but close. Now we're going to, theoretically, that should be fine. We're going to badge all of this for 2D meshing. Execute. We're going to make a independent region. Create, assign parts to regions. Create a region for each part and a boundary for each part's surface because we have a bazillion different parts. We are going to automated mesh concurrently all of them. So the wall control will be on our run up down. Our fin control will be on the air side for all of these fins. The max size is on the air on the plane. The inlet outlet control is also on the air on our inlet outlet. What else? We want new surface control. So on our fins, we want no boundary layers. None. We also are going to want to probably make the sizes smaller, as well as customize our surface proximity. So disable prism layers. We're going to probably want to make this 25%. Ooh, that's small. 2.5%. 2.5%. Yeah, sure. Surface proximity will do 5. Search ceiling is 0.02, so 2 millimeters. Execute. Oh, crap. I messed something up. Important. You need to check that box if you're doing a bunch of parts separately. So it finished all 20 fins. Now it just needs to finish the air. And we'll see what this mesh looks like in just a sec. Now, the important thing is, since I deleted my region, all of these just broke. So I need to tell them that we're talking about the air region again for these derived parts. I need to tell it that we're talking about the fin areas. Um, yep, there we go. Temperature inlet, temperature outlet. Let's see here. Air inlet regions. Air outlet. What time is it? 12 o'clock? Okay. I need to start wrapping this up soon. But sometimes it's easy to get interested in doing a problem and lose track of time. So one thing is, by doing this, we have a whole bunch of interfaces. So the fins are actually modeled separately as separate parts, and we are going to tell them to simulate the fins as solid geometry. So we need to define the physics used for solid geometry. So this is two-dimensional solids. It's going to be steady. They're going to be solid. It's important. And we need to track their energy. So segregated solid energy, constant density. They're not going to change temperature on us. Don't need to worry about anything else. That should be fine. Now we need to tell it what type of solid. By default, these are aluminum, so that's probably fine. Pure aluminum. I mean, let's see what materials they got here in the standard database. You could obviously define your own, but in the standard database, we have aluminum alloy, which is probably closer to what it actually is. Yeah, we'll go with an aluminum alloy. It's probably considerably closer to what it actually is. And we're going to tell it, hey, for these 20 bodies, which are all the fins, you're going to use physics 2. You are... I was thinking about it. You are solid bodies. No, I'm still thinking about it. If you click and STAR-CCM kind of doesn't do anything, it doesn't react like you'd expect, it's probably thinking about something. You might just want to give it a second. If you keep on clicking, it's probably going to not like it. So, and I'm actually going to create a parameter here. New scalar. This is going to be units of power. 1. We're going to tell it 2,000 watts. And we're going to call this dissipation. And how we're going to do this is we're going to tell it collectively, all of these have a energy source. Each of these fins are independently going to generate 1/20th. Actually, it's probably one. There are 20 of them. Yeah, I'm going to say 1/20th of the total dissipation. So we're going to say dissipation divide by 20. Okay. So now, theoretically, these guys should dissipate, well, a significant amount each. They should dissipate about 100 watts apiece. Solution, clear solution. I need to set boundary conditions for the air. So what else? Our inlet and our outlet. So our inlet is, well, the velocity inlet. Our outlet is a pressure outlet, and we will let our inlet be 3 meters per second, let's say. I do, however, need to recreate these scenes a little bit because we got rid of the region. So I need to add the region back in. And I'm actually interested in all of our regions. I'm interested in not just the temperature of the air, but also the fins themselves. So notice there's no gaps in the middle here anymore. And oh, hey, look, we have a whole bunch of air, and then we can very clearly see our fins. Let's see how rapidly this goes. Well, it's a lot slower because we have probably a lot more fins here. Let's see here. Where's my residual graph? Oh, it's just running a lot slower. Is mostly because my count went way the hell up for how many cells I have due to the fins. Did I ever look at another mesh scene? I don't think I did. Let's see how crazy this is. Scenes, new mesh scene. Yep, and this is the mesh inside of the fins. You even see there's a fin right here. Look at that. So, how many total cells do we have? We have well, across the entire. It's not actually all that many. It's like in 125,000 ish. That's not a colossal amount. Um, 9995. Let's see if this might make this unstable. Let's find out. Yeah, so the fins are actually heating up. You can see 305, 306, 307. So it's kind of looking for equilibrium. And just this is running a lot slower, but also it's going to take probably considerably more iterations to converge than it did previously. But what it's actually doing is there are no real boundary conditions in here. This is purely saying, hey, I have a solid aluminum fin. I'm generating heat. And you can actually see the fins have a temperature gradient to them, right? They start out relatively cool, and then they increase in temperature towards the back. And then these fins out here are just blisteringly hot because they only have one side. So actually what I should probably do is say that this is divided by 40 for the end. And what I should also say is this is divided by 40 for the other end, because technically they only have one side. This other side doesn't allow heat flow through it, so that's going to be problematic. So to kind of keep them all more or less at the equal dissipation through each face, we need to effectively have these dissipating half the amount. Now, one thing to note is technically this isn't dissipating 2,000 watts. It's dissipating probably about 1,900. So technically, if I wanted to dissipate exactly 2,000 watts, I would need to slightly increase the dissipation of all of these. I would need to actually be dividing by 19 and then divide the end ones by a factor of 2. So technically, I slightly violated the dissipation I was after, but we're not actually after a specific dissipation per se. Let's see here. XY plot. That really doesn't tell us if it's changing at all. Yeah, see, the temperature is still changing. You would want to wait until this completely flatlines, which may or may not be before these residuals are done. But this is a thermal interaction between solids, the fins, and the fluid that is taking thermal dissipation. It's adding heat to the fins, about 100 watts, a little bit less per fin, and ultimately it's saying, hey, the solid, like the solid warms up, you're adding heat to it. The solid is touching the air, so some of this heat gets transferred to the air. The air heats up and carries that heat away. So this is a solid fluid thermal interaction of a fairly typical cooling stack. You have thin metal plates of aluminum with air flowing over them. There is some heat dissipation on the plates, on the fins, and the air is carrying that heat away. The fins tend to be much cooler on the near side to the air source and are significantly warmer on the far side from the heat source. And then it's just going to take its sweet time to reach equilibrium. So, again, that's a little bit more of an advanced topic, solid fluid thermal interaction, but is pretty common in a lot of applications where you would need to do this. So, or where you might be interested in the temperature of the solid. I think I'm going to leave it there. I've been at this for, damn, almost 2 hours now. Shoot. Okay, I'm going to leave it here, and hope everyone enjoyed the video, and I will be back next time for trying to think of what it would be exactly. Probably some more, maybe a little bit more thermal stuff, and I'm probably just going to throw up a bunch with some various advanced topics that won't necessarily show up and you won't necessarily be asked to do, but you might find them interesting.